Founded in 1962 as a school of theology, we have grown into a university in 1985. Our journey reflects the strength of our historical roots and vision for a brighter future. As a sustainable entrepreneurial research university, we focus on creating solutions, nurturing entrepreneurship, and advancing research that impacts society. Guided by faith, driven by integrity, and committed to excellence, Duta Wacana prepares graduates who are ready to serve the world.
With 7 departments and 17 study programs, including master's and doctorate degree, we are committed to academic excellence. Our students aren't just learning, they are growing as leaders, innovators, and changemakers. With state-of-the-art facilities and a vibrant student life, we make sure every student is ready to take on the challenges of tomorrow. We prepare students for the global stage, offering facilities and opportunities through various international programs. Our commitment to inclusive education ensures that everyone, including those who are impaired, has a place to grow and succeed. Duta Wacana. We honor our past, embrace the present, and look forward to a future where knowledge, integrity, and service shape the world. Join us on this journey of excellence.
As the world we live in keeps on evolving, we become more reliant on technology. From businesses to our everyday lives, everything needs to be easier and more efficient, so that we're able to utilize our precious time better. We created technology beyond space and time and made everything possible. So who made it? Glare.
Us?
Yep. They are the creators from Glare, the top minds of the country, professional, creative, and always innovative. Glare, your technology partner, to help you accelerate and be efficient. We integrate the things that you always wanted to have in your business, such as AI, cloud, mobile, most importantly, in a secure and affordable way. Hey, Michelle.
Oh, hi!
Can you tell me what solutions Glare provides?
For sure! We provide quite an array of solutions. Let me show you. Here's a great way to arrange your product display. Hi, Sheila!
Oh, hi!
With Planogram, you only need to take a picture of the display and instantly your layout is checked. so you can determine the best layout for your display that can increase sales in a cool way.
Absolutely.
Want to know how you can maximize your inventory? We have demand forecasting, a technology that can predict the demand of your products in the market. Being an integrated system, there will be no more inventory challenges in your supply chain.
It's all connected.
The future is here! With OCR technology, all you have to do is scan your documents, then all physical data will automatically be digitized at your fingertips.
Shortly, so please kindly sit it at your table for those who just come to this auditorium. Good morning, distinguished guests, respected speakers, and dear participants. Welcome to the day 2 of the 28th International Conference of Oriental O-COCOSDA 2025, held here at Universitas Kristen Duta Wacana in Yogyakarta, Indonesia. My name is Anti, and I will be your Master of Ceremony for the program this morning. And it's a pleasure to be here with all of you this morning and to be part of this inspiring gathering. We hope that everyone had a productive and enjoyable first day of the conference, and today we continue our program with another series of inspiring sessions, presentation, and discussion, all reflecting our shared commitment to advancing speech and language technology for Oriental languages. To begin our program this morning, we start with the second keynote speech by Dr. Nancy F. Chen, and to lead the keynote session, we are honored to have Professor Satoshi Nakamura as our moderator. Professor Nakamura is the Presidential Chair Professor at School of Artificial Intelligence, the Chinese University of Hong Kong, Shenzhen, China. He earned his bachelor's degree in electrical engineering from Kyoto Institute of Technology and doctorate in information science from Kyoto University, Japan. Professor Nakamura research covers fundamental speech technology, multimodal interaction, and applied data science, area which he has made contribution for over 3 decades. Throughout his distinguished career, he has served in numerous leadership and academic roles, including as Director of ATR Spoken Language Communication Laboratories, Director General at the National Institute of Information and Communication Technology, and full professor at the Graduate School of Information Science and AIST. And his remarkable achievement has earned him numerous national and international awards, including recognition from the Acoustical Society of Japan, the Information Processing Society of Japan, IEEE, and Google AI, among many others. So, ladies and gentlemen, here in front of you already Professor Satoshi Nakamura and also our keynote speaker, Dr. Nancy F. Chen. So please, let's give a warm welcome to both of the keynote speaker and also the moderator.
Hello. Good morning, everybody. It's a great pleasure to chair this keynote session. My name is Satoshi Nakamura. Thank you very much for the introduction. So today we have the keynote speaker, Dr. Nancy Chen, and let me introduce her. Nancy Chen received her PhD from MIT and Harvard in 2011, conducting research at MIT Lincoln Laboratory in multilingual speech processing. She currently leads research in conversational AI and natural language generation at the Institute of Infocom Research, I2R, ASTA, Singapore, with applications in education, healthcare, journalism, and defense. Her team's speech evaluation technology was deployed by Singapore Ministry of Education to support home-based learning during the COVID-19 pandemic. So she led a cross-continental team on low-resource spoken language processing that ranked among the top performers in the NIST open keyword search evaluations. These are 2013 to 2016. Dr. Chen is a recipient of the numerous honor, including the 2025 ISCA Fellow this year. The Singapore 100 Women in Tech 2021, and the Best Paper Awards in SIGDIAL and APSIPA. And L'Oreal UNESCO for Women in Science National Fellowship. She serves as the ISCA board member, program chair of iClear, and has held editorial roles in several top journals and in speech and language processing. So she's going to talk about the recent activities in your team, right? So please welcome Dr. Nancy Chen.
Thank you. Should I? Okay. So we'll load up the keynote slides.
Who will switch to? Is somebody to?
Okay. So good morning, everyone. I'm very happy to have this opportunity today to share with you some of our recent work. So I'll be talking about the art of listening in artificial intelligence, but coming from an audio and speech angle of how sound makes a big difference, whether we know it or not. So I've been also pretty busy with a lot of international research leadership activities. So next month I'll be at NERA IPS in San Diego because I'm program chair this year. So if any one of you are going, so let me know. And just met some of you at the Netherlands for Interspeech for ISCA Fellow. Yeah, so first of all, I would like to share. Are we able to remove the top thing? No, is it? The top thing is.
So is there?
Is it possible to remove the top? Okay,
yes.
Good. Yeah, so here I want to start with this slide. So I had a friend that I admire a lot. So he always wins any argument with his wife. And he does this by taking off his hearing aids. So he was born with some hearing difficulties, so he cannot hear anything below 500 hertz. So basically, most sounds don't sound the same to him and us. He's very smart. And so for him, he has the superpower that whenever he doesn't want to listen to anything, he just takes off his hearing aids. Immediately, no sound comes in. But for most of us, we cannot do that. When you see a scary movie or you're on a roller coaster ride, you're very scared, you can immediately shut your eyes, and it's an intuition. But for sound, it's always there, whether you like it or not. So right now, you're here, so if you think what I'm talking about is boring, you still have to, kind of tolerate it to some extent, because you cannot fully make sound not enter your ears at all. And there are evolutionary reasons for this, because it helps us alert to different dynamic changes in the world. So whenever we hear birds chirping, it makes us feel calm. There's a biological reason behind this, because usually if some kind of big earthquake or volcano eruption is happening, a lot of animals are much more sensitive than us. So they're aware, so they'll stop singing. They need to quickly fly away or something. So to us, when we hear the birds chirping, then we know things are probably not bad. But if these things are not there, these are little clues to us that we might need to be more careful. Then your heart rate might go up to prepare for different types of things that might happen. And this is all happening in the background, so you may not be aware of it, but it's constant processing in our brains. Okay, so this emphasizes the audio and speech importance in a lot of our intelligence as human beings. And so here I wanted to start with a manga strip that I read when I was a kid. It's a little older than me. So basically, we see that Doraemon, this future robot cat, this robot cat from the future, has already foreshadowed what we see in generative AI almost half a century ago. So he came up with this box, and you can put a manga book in this box. Then this box will learn the artistic and writing style of this manga artist. So then this box is adapted to this style. So then you can give further instructions and say, I want a new manga book by this artist. I want it to be the topic of sci-fi and space exploration. I want it to be sad and happy, and then it can all do it. And so then you have a new manga book. So this is kind of what's happening in the AI world, and it's actually something that you might have already seen in science fiction and comic books. Yeah. So what's behind this, right? So behind this is the foundation models, and foundation models, you might often hear it as large language models. So they're often interchangeable in the sense that large language models is foundation models' first success story. And now you see a lot of multimodal large language models, but they are largely taking advantage of the text large language models that are being used as well. So basically, with this foundation model, you can have different types of data. Multimodal can be text, could be speech, could be music, could be 3D signals, could be video. And then it can do a number of tasks that could be very different. It could do sentiment analysis on social media text to tell you if someone is angry or upset. It can generate captions for images. So so this is foundation models. And so before we move forward, I want to just take a couple minutes to summarize the story of AI for the past 30 years. So if you want to just use two words to summarize it, it would be emergence and homogenization. And they both enable scale, and that's why you see a lot of changes and a lot of that's across the board, very penetrative because of this scale. So emergence means that the behavior of a system can be implicitly induced rather than explicitly constructed. Homogenization means you consolidate methodologies across different applications for machine learning systems. So it might still sound very abstract, so I'm going to give some examples. So in 1990s, when people talked about AI at that time, people might refer to expert AI systems. So a lot of the work was trying to explicitly code out the rules for each expert AI system. But that was very time-consuming and exhaustive, and a lot of this knowledge may not be easy to explicitly write it out. So with the emergence of machine learning, you can learn how to do this implicitly. So implicitly learn the rules through learning algorithms. And the learning algorithms could be the same for different tasks. So an example could be hidden Markov models. You can use it for speech processing tasks, also image processing tasks. So a lot of the work as a researcher would be to figure out how to make the features better suited for the task you're working on. So if it's from speech or audio, if it's speech, for example, you might imitate how the human auditory system processes information, where our auditory system is more attuned to lower frequency sounds, more sensitive to those, and less so for higher frequency sounds. So you embed these characteristics into the features used for speech processing tasks. For image processing, if you want to do object recognition, then our eyes are very, very sensitive to the edges of the objects. So you need to make the edges, the features there, more enhanced to help you with this kind of task. So you need to do a lot of this kind of feature engineering to help with the machine learning systems to make the performance better. So this went on for 20 years, and then in the 2010s, the deep learning revolution came about. This is the second time neural networks made a big wave in AI, but this time it stayed strong. So here, we no longer need to specify the features for the different tasks because the deep learning systems, the neural networks, are able to learn hierarchical features that we need. So then you reduce the domain knowledge needed to build machine learning systems and applications. And on the neural architecture side, it also became consolidated, where now for all the different tasks, for example, in computer vision, the classic example is convolutional neural networks. Now for the same convolutional neural networks, I can use it for different tasks in computer vision. It could be image matching, it could be caption generation, it could be object recognition, all with the same neural network architecture. So then in the 2020s, we reached a different era, a new era of foundation models, where now we can actually implicitly learn functionalities that I mentioned in the previous slide. So it could be caption generation, sentiment analysis, summarization of documents. And so one classic example of how it's consolidated is with models like GPT-3. And so this is what we're seeing now. Okay, so behind this is a language model, right? And it's actually a very classic word guessing game that we've been using as humans a lot. So let's say you are, so here, let's say just now someone walks into the venue and slammed the door, so you couldn't hear part of my sentence. So, but you heard the first word, thank. Then you could guess, the next word could be you, could be me, could be God. And without any other information, here you might choose, oh, she said thank you. So this is what we do all the time. You could speak more than one language. Let's say you speak Indonesian and you speak English. So if your Indonesian is better, then when you have words that you didn't hear in a sentence, you're more likely to figure out what they were because your Indonesian language model is stronger. Yeah, so this is what our brains do. We fill in information to help us better understand all the time with all the cues we have. So on the computational side, this is not something very new. A lot of people got more aware of it because of ChatGPT, but actually the history of it from the computational modeling side started more than a century ago. So back in 1913, when Markov chains were developed, statistical n-grams were used to predict if the next letter in ancient Russian literature was a vowel or consonant. So Markov chains should be very familiar to a lot of you. In Shannon's information theory that underpins all of the digital technology that we enjoy today, it also used statistical n-grams. So in Shannon's case, it used statistical n-grams to predict for an English word what might be the next letter given the current letter. Okay. So this influenced many fields, so psychology, engineering, linguistics, all been impacted by the idea of statistical n-grams. But a very influential linguist, Chomsky, didn't really like the idea. He thought it was an engineering hack, and this stalled some progress for a while. But then in the 1970s, actually, we had a comeback, and this is in speech technology. So this is one of the most famous examples in speech technology history of commercialization. So IBM and CMU developed it at similar times, and for CMU's Dragon Naturally Speaking, it was acquired by Nuance, the largest speech recognition company at that time. So the idea back then was that actually it's different from now. Now we could use a lot of different types of speech recognition software very easily. Even if you turn it off on your phone, it still secretly does it. It's a little annoying. But back then, it was a very hard problem to tackle. Because let's say I say two sentences, I love language models. And then I say it again, I love language models. So although to you, the human ear, it sounds like exactly the same thing, actually it's two distinct acoustic signals. Okay, so how far away my mouth is from the microphone would influence the final acoustic signal that reaches your ears. Right? So the air pressure that I cause with my vocal folds vibrating and my tongue moving, all of this will interact with the environment around it and the recording device. So there are other factors that could affect it. Let's say I suddenly got distracted and I was like, oh no, I forgot to add something to my slides. So then this top-down cognitive processing will also change the acoustic signal. Let's say I needed to drink water, so in between the two sentences, I drank water. So the hydration in my vocal folds will also change the acoustic signal. So all of this is to say that the acoustic signal has a lot of variations that are natural variations that our ears are very used to. But it makes it very hard for the machine to decode what is the underlying words that I'm trying to represent, because the acoustic modeling part is not trivial. So here, with the help of statistical engrams, I can help narrow down the possibilities of what the possible words that I'm trying to say are. And so in this situation, they took advantage of certain commercial applications where you just need to say a string of digits. So this could be your passport number, your ID number, it could be your telephone number. And with engrams, statistical engrams, you could drastically reduce the entropy. So originally, the next token, there's like millions of choices. Now it's only 10 choices, 0 to 9. So with the help of language models, then these technologies we built for speech processing could now be commercialized. And so this was a very big success. And so it helped progress a lot of what we see now. And so, but with statistical modeling, one problem that you often face is that it's very hard to predict the words you didn't see in your training data. Because if you go by it, they should have 0 probability, but we have limited resources during training. So a lot of the algorithm development at that time focused on smoothing. How do I assign some non-zero small probability for all the unseen words that I cannot capture during training? And this is a very common and realistic problem because in language there's a long tail problem where a lot of words are there, but they don't occur very frequently. So how do you model this long tail effect? And so there are different toolkits that have been developed. So one of the more popular ones is SRILM. So it's a good friend, Andrea Stocks, that developed it at Stanford Research Institute. So in the same time, speech processing has benefited from neural networks a lot. So even during the statistical machine learning era, we knew that taking features from trained neural networks and augmenting it to whatever you have helps boost performance a lot for acoustic modeling. And so for the language modeling side, there's also a lot of endeavors to try out. So Bengio was one of them in early 2000s. Some other very famous work include recursive neural networks, RNNs, LSTM, long short-term memory language modeling. So here, the idea is that because for language, it's a sequential signal, what I'm saying now depends highly on what I said before, but how do you model the neighboring words in a way that makes a good trade-off between memory and how it can boost accuracy has been very key. So then this continued. So on the natural language processing side, actually it has been like, didn't really take off very fast until vector representations, because in the text side, you need to deal with discrete symbols. So the discrete symbols are words, so it's very ad hoc. And so how to incorporate that into computational models that are very used to numeric representation was a little clunky. But the introduction of vector representations, where you took advantage of all these continuous numbers that represent language from the neural networks, although you don't know how to interpret them very well, helped a lot with NLP processing, because now you can take advantage of all these tools that everyone else in the computational field has been developing for all the continuous signals that have continuous numbers. So some classic examples are word2vec and Glove, and we now see a lot of variances of it that are still being used. So this was in the 2013-2014s when NLP started to take off a lot faster with the deep learning wave. Then transformers were introduced in 2017 by Google. So this is still the building block Lego piece for all the large language models you see now, because it solved a very practical problem of where you could attend to all the key information in your input very dynamically while doing parallel processing. So you solve two problems at the same time of trying to attend to neighboring information while getting efficient compute. So at the same, very soon after, BERT came out from Google. So to me, this is actually when large language models made official scene to our field. So the key behind BERT is self-supervised learning. So for a very long time in machine learning, we always knew unsupervised learning is much better, supposedly can generalize better, but it's very hard to outperform self-supervised learning because for self-supervised learning, you often have a scale problem of how much annotation you can get. But in the case of modeling semantics, so people figured out, actually, I can take advantage of all the texts on the internet that are supposedly free because of the advertisement model we went with internet. So all this text you see online is actually annotation of human language. And we trained all these students to go to high school, to go to university, and then they start posting on social media, they start editing Wikipedia articles, and all of this contributed to all this text annotation we have. And so with a very brilliant setup of using all this information and tactfully taking out some information, let's say the last word of the sentence or any words in the middle of the sentence, and asking the computational model to guess what the next word is, help train the computational model to understand semantics in an implicit way. So now you don't need extra data because you already have a self-supervised way of learning semantics with the data you already have, so you don't need extra annotation. So this solved a very big problem in linguistics because for a long time, people were able to tackle syntax, the rules of the word ordering, word structure, and then through physics, we could tackle phonetics to understand the physics of sound or speech sounds. But for semantics, because the ground truth is subjected to everyone's brains because of your different backgrounds, it has been very hard to tackle. But through this implicit way, we could analyze all the words on the internet. So you can analyze all the neighboring words of king and queen, and then realize that they share a lot of similarities in their semantic representation. The only contrasting relationship they have is gender. But they share semantic features of authority. You can do the same thing and take all the sentences with princess and queen and analyze all the neighboring words. Then you can come up with, they share a lot of semantic similarities, but they share a contrasting relationship of senior and junior. So then you can basically learn the meaning of words very elegantly through this way. So this is self-supervised learning, and then after BERT, many other language models came out. BERT is more suited for language understanding. There are other ones for language generation. So this came out in 2018 on arXiv. After a year, it received the Best Paper Award at NACL, and it was, to me, for all the NLP people working on it, knew the era is different now. But this is confined to a very small population of NLP nerds. So in November 2022, when OpenAI released ChatGPT, it has a very easy user interface to use. And everyone else that you may not even be an engineer or researcher. You might be a politician, a manager. You can go try it out. And everyone was quite impressed by the progress. But it's not just OpenAI. It's not just these couple years. It's been more than a century of work that has made this possible. And so afterwards, there are a lot of multimodal counterparts, and then there's also a lot of models from different companies. So Gemini, there's DeepSeek, There's also other variances and some that we're developing for the Southeast Asian context that have come about. Okay, so this is a historical perspective to remind people that this is not a new thing, and a lot of research and development has gone into what we see now. Okay, so here I wanted to quickly talk about generative AI and agentic AI. So for generative AI, the core generative capabilities are pre-training, instruction fine-tuning, and alignment post-training. So for pre-training, it's basically equivalent to someone reading a lot of books. So you're building a lot of fundamental knowledge. But let's say after reading a lot of books, I want to develop skills. Okay, so let's say I want to develop skills like public speaking. So then you need a second step, instruction fine-tuning, where you convert the knowledge to task-solving skills. So reading a lot of books and being able to speak in public are related but different, right? So then you might need to practice more speaking. You need to not just think, you need to talk, okay? You need to think about what you want to talk. But then when you give talks, let's say now I'm here in Indonesia for an academic conference. This will be very different to briefing government officials at United Nations. So then I need to do human-centric adaptation. So on the AI-LM capability terms, it's alignment post-training, where I need to adapt to the different cultures. So some of the cultures is the social cultures. Some of it is because the setting is different. So all of this need to be accounted for. So there's Gemini, there's Mistral, one of the first open source ones from Europe, and then on my research group side, we have Lion. I'll talk about it later. But this is the core AI capabilities for training the AI model of large language models. But once you have the large language models, you can do resource-efficient adaptation. So a lot of times you need domain knowledge integration. And now with the model's capabilities, you could do few-shot generalization. And so once you have these large language models, you might have more than one. So how do you use them in collaboration to help you solve more complex tasks? Can help enable agentic AI, where the AI is more autonomous. It can figure out a lot of the details on its own, so it's easier for you to use for applications. Okay, so the users could be government agencies, could be startups, could be individuals, could be big companies that want to go into AI. Okay, so before I move on to talk about some projects that we've worked on, I just want to quickly show this slide of AI reasoning and grounding. So we've made a lot of progress on the AI reasoning side because it helps us draw inferences, makes decisions, and problem solving. But a lot of what we might also need is the grounding part. So how does it connect to the real world instead of just being supposedly smart? So one is the multimodal sensory embodiment. So a lot of the AI reasoning is still focused on text, but the real world is full of these different modalities of audio, speech, video, and then different movements. There's smell, there's touch. All of this helps us embody the information and contextualize it, so this is important. And then there's human expert reinforcement learning. So some of this has been done in the AI reasoning training, but a lot of times we need more domain-specific experts. It could be from the medical field, it could be from the education field. And then while we try out the technology, we can do real-world data cross-check. So these, I will also share some examples later. Okay, so here I will talk about 3 different types of examples that are across domains for our multimodal generative AI. The first one is for digital services, so I'll focus on multimodal grounding, reasoning, and learning. So it's called Lion. So Lion has 2 meanings. The first one is Mera is red in Malay, and Singapura means lion city, so it means red lion, basically. On the technical front, it's multimodal empathetic reasoning and learning in one network. So, and it's a first multimodal large language model developed for priority of putting Southeast Asian context in mind. And so I'll use this traditional Chinese character to spell out the different components of Merlion. So the first part is the speech audio encoder. That's the red part. It's your ear. So you use it to listen and hear. And then the blue part is the vision encoder. So to be a good listener, you need to have good eye contact. Right? So vision is important even when you're just listening. Okay, and then together you want to integrate the different modalities. And then on the thinking part, usually people only talk about the analytical side, the analytical decoder, to emulate how you think. But we also want to bring in the empathetic side of using your heart to feel. And this ties in very nicely with the multimodal aspect, because sometimes it's easier to have misunderstanding when you just do text messaging, but when you can hear the other person's speech, you can hear the intonation, the emotions behind, then it's easier to interpret intention and understand each other better. So the empathetic side ties very closely with the audio and speech information that we can get. So in Merlion, what we're trying to do is, in addition to modeling what, we also want to ask the questions of why. And it can help us in different types of tasks, including audio scene understanding, where you make sense of physical sound sequences. Could be voice characterization, so it helps you understand or infer the person's background. Could be gender, age, accent, and emotions. And then we use speech to communicate with others. So when we talk with others, there's different types of spoken language comprehension that we should be aware of. And together with this, it brings in another dimension of social dynamics and cultural nuances to help us with multimodal contextual reasoning. So I'm going to try to play the first video here. It's deliberately small so it can focus on the sound. Is the audio working? So here you heard, you had the video, but you heard sound of water, maybe getting louder and louder, and eventually maybe wood hitting sound. So it might sound very random, but actually, if your AI is smart enough and hears this, you might want to ask it, is it really random, or there's actually ancient technology behind it? So it's a version of a scarecrow. So a scarecrow looks like a human to scare away animals, but in this case, it's using audio, because you can hear audio from far away, right? And then so it sounds like, to us it's like maybe pretty random, but to animals, only humans produce sounds like this, right? They might like to use water, and then they have tools, so they'll make these sounds of bamboo or wood hitting. So then it scares away the animals. So it's intended to scare away animals like deer that might come damage your crop. And so if your AI is a little smarter, so just listening to these sounds, it can not only infer what the sounds are, but actually where it might happen. So it might happen in some areas in Japan where there's a rich history of agriculture. And there might be like big animals like bears and deer around. And so we want the AI to be this intelligent. Okay, so this is on the pure audio sense. Now I'm going to give another more social example in the next slide. If it works. Okay, can you help?
Can I get a kopi kosong?
There's no kopi kosong. Kopi is with condensed milk. Kopi siu dai has less condensed milk. Kopi C has evaporated milk and sugar. Kopi C kosong has evaporated milk and no sugar. Kopi O has no milk, only sugar. Kopi O kosong has no milk and no sugar. You understand? So there's no kopi kosong. What you want?
So if you didn't understand the Singlish conversation just now, it's okay. You're just as smart as ChatGPT, and I'll explain a bit more of how we want the AI to understand it. So here is one question of, if you want to order a drink in Singapore, which one has the highest calories? So ordering coffee and tea in Singapore is not trivial, and we might share some of this in Indonesia as well. So I'll just walk through what are the multicultural reasoning steps we need to go through. So the first part is the multilingual understanding part. So day is actually from Hokkien. It means tea. So actually the Fujian province in China is where tea originated. The British really wanted to do business with China, and so brought the tea all over the world and called it tea instead of day, because day is too hard for them to say. And so then we know tea as in this form in general, but actually has multilingual roots. And I think in Indonesian, day also means tea. And then there are other phrases like shou dai. It came from Cantonese or Hainanese. It means less sweet or less sugar. And then kopi is from Malay, and I think in Indonesian that also means coffee. So it has Arabic roots. And so this is the multilingual understanding part. Then there's the cultural and personal preference part. So day, in the Singapore context, because it has a lot of Western influence as well, it actually means tea plus condensed milk plus sugar. So this is different from the original Chinese tea, where it definitely doesn't have milk and sugar. And in Japan, tea will usually by default mean green tea without milk and sugar as well. So how you interpret what the default setting is different across cultures. So for the example in Singapore, if you don't want milk in tea, you need to further specify it and say de o. So because o means black in Hokkien, and when tea is more black, it means there's no milk. Okay. So similarly for coffee, kopi means coffee plus condensed milk plus sugar. So if I don't want condensed milk, I want evaporated milk, I need to further specify and say kopi C. Okay, so the C came from two sources. One is traditionally a lot of people at the coffee shops use this Coronation brand of evaporated milk with a prominent C on the can. But it also has a similar sound to Mandarin's word for diluted and thin. So this is the cultural and personal preference side of how the language could be different. Then on top of that, you need to do reasoning with dietary knowledge to know that condensed milk is sweetened, and sweetened means there's sugar, and sugar means there's calories. So if you want to higher calorie intake versus lower calorie intake, you need to specify differently of what you want. So this is one example of our work in CEVAL, where we looked into different Southeast Asian cultures and compiled data sets like this to do benchmarking for large language models. And there's some gap. And I believe this example resonates with different cultures within Southeast Asia that all have different types of proportions and multicultural components. So this is one example. And so here I want to bring about another thing why we want to build large language models are end-to-end. And so one reason is because if you have cascaded models, you will propagate errors. So here I'm going to show a Singlish example. So let's say I say the sentence, Bojo, you went to the movies without me. So Bojo actually comes from Hokkien. It means the fear of missing out. It implies that I have a reasonably close social relationship with the person I'm talking to, because I'm kind of shaming the person in public. I'm saying, next time if you don't go to the movies without me, it really means you're not a good friend. So it's a bit passive-aggressive. So you will not use this word when you're talking to your boss's boss that you just met, right? So although it's only 5 letters trying to spell out the sound, it has very rich meaning of the implications of the relationship and the expectations in the social sense. So if this sentence is passed to the best speech recognizer out there, or claimed to be out there, it will return the string underneath. Bonjour, you went to the movies without me. So because the best match it can come up for bonjour is bonjour. French, it's in French, it means good day. It's a greeting word in French, and it usually occurs in the beginning of the sentence. But it completely misses all the meaning and nuances that I was trying to convey for many, many sentences before this. So once you lose the meaning, you lose it forever. Then you convert it to text, and you use it for all kinds of processing, and you don't get the original information. So here what we want to do is have a model that can learn the semantics from the multimodal sense in a very unified way. And for these spoken paralinguistic nuances, we want to pay special extra attention to it. So here I have another Japanese example. Kawaii ne. This ne is highlighted in pink. And so it means it's cute, isn't it? Pokemon is cute, isn't it? But it also is implying I am inviting my friend to chime in, and I'm expecting her to say, oh yes, I also think Pokemon is very cute. Okay? So in this example, in Japanese, we have a formal word writing system to specify this ne, this meaning. So it helps the modeling. But for a lot of our languages, it's spoken. We may not have a formal way of representing it on text. And this might pose additional challenges when we do computational modeling to try to integrate the different cultures, the different social dynamics in our modeling. And so this is something I want to bring attention to, and a lot of you might have similar experience, and we can work together towards this. So then if we can model this semantics and pragmatics and emotion information more comprehensively, then it can better enable all the downstream tasks of audio, scene understanding, voice characterization, contextual reasoning, and then it can minimize error propagation. So this is the example for Mary Lyon. So a quick summary before I move on to the next one is text data alone can't model the world completely. So a lot of sensory modalities like audio, video, and sensors can enrich the multimodal reasoning part. For the North American-centric AI models, it misses global needs, and we're more acutely aware of the Southeast Asian needs. And then developing approaches that are end-to-end helps us with better multimodal contextualization. Okay, so now I'm going to move on from Mary Lyon to education, and this is a very apt place to talk about it, given that we're at a nexus Center of Culture and Education. I heard there are 4,000 students here, many, many schools. And so I'll share some experience from our side of developing AI technology for education. In this case, it's for very young kids. They're 6 or 7 years old. And we need to focus on data efficient learning for streamlined deployment. So this is a multimodal, multilingual AI tutor for children. So to give some context, in Singapore, there are 4 official languages. English is used in government, in education, law, commerce. But there are 3 other languages, Mandarin Chinese, Malay, and Tamil. And so people, when you're a child in primary school, you need to choose the language that correlates with your ancestors' culture the most. And you will take extra courses on that. And so one problem for Singapore is, so Singapore is an immigration society. Most of the Singaporeans now that are in elementary school are maybe 3rd or 4th generation immigrants. So their parents probably grew up speaking in English, in both the household and outside the household. Their grandparents might have been like that too. So there is a disconnect where originally there's a lot of multilingual advantages for Singapore where, if you know the languages well, it's easier to establish diplomatic and business relations. But because it's how the immigration society has developed, now they're losing that edge. So for all of the academic performances, when you compare across the world, Singapore is always very top, whether it's English writing or math or science. But for these 3 languages, it has been dropping and dropping and dropping for the past 20 years. And so Singapore is a very small country. It doesn't have a lot of human resources, not enough teachers. So it wants to use AI to fill in this gap. So this is part of how we're trying to help. And so for Singa Kids AI Tutor, right now it's being featured in Singapore's 60th birthday in all the national libraries. And so I'll take a deeper dive into it. So this is the Gen AI architecture for Singa Kids AI Tutor. So there are 3 parts: the multimodal understanding part, the multilingual large language model part, and the multilingual speech generation part. So in this case, because it's for very young children, it definitely needs to be a speech technology application, because these children may not even know how to read and write yet, so and not use the computers so well in typing yet. And also, we all know for language learning, being able to speak and listen is very key to the development. And it's actually how you might use it a lot when you grow up as well. So being able to do well on tests doesn't really fit the bill. So here the task is that you have an image, and then the child will need to describe it, and the AI tutor might ask questions about it. So then you need to do scene comprehension to understand the image, and then you also need to understand what the child said, and then you need to do evaluation on the speech to understand if there are mistakes. It could be from the pronunciation front, it can be from the vocabulary front, it could be from the ethics front. There are many things that might need to be evaluated. Then for the text LM part, it needs to integrate the education philosophy. So, for example, you might want to be more encouraging for the students to learn, so you need to provide scaffolded guidance. So I'll give some examples. Then for the speech generation part, you want to be able to enhance engagement so there's more motivation in learning. So here is one example of the image that could be the input to the AI tutor and to the child. And so here to understand if the AI really gets what the picture is about. So here is a sentence: the family consists of 2 adults and 2 children, all wearing traditional Malay attire. And we want the AI to box out the text description in the image. So if you use a more North American-centric model, like here in this case it's Apple's ferret model, it gives you the red box, where the daughter and the dad is missed out, is not part of the family. So our model is more attuned to these multicultural factors, so it gives you the blue box, so the whole family is included. Okay, so cultural factors could include age, where children are often a minority, gender, and ethnicity. And so here, before I move on, I wanted to quickly show the AI performance gap across languages. So this is done on ChatGPT. So the vertical axis is the accuracy. The green axis is the semantics, where the same instruction, you say it in different ways, but it's the same meaning. And the orange axis is the multilinguality part. So here you can see the very top plane is green and it's English. Notice it's not flat, meaning that there is variation. So depending on how you ask the question, it may or may not give you the same answer. Then the red plane is Mandarin Chinese. So there's a reasonable gap. Is there a connection problem? There's a reasonable gap, so I think the gap is closing, but you can see here that English still performs better overall, and the red one could be bumpy, but it might be smoothing out. The silver one is Spanish, and then the yellow one is Vietnamese, followed by Indonesian and Malay. So here, this ordering correlates strongly with the quantity and quality of the data suitable for training. Yeah, so here we ideally want all of the languages to be the same on the top and not bumpy. Yeah, so we're trying to close this language gap. So here is another way to visualize this, incorporating our modeling. So here, the horizontal axis is the English capability. The vertical axis is the multilingual capability, so this includes Chinese, Malay, and Tamil. In our case, we focus a lot on Malay and Tamil because they need boosting too, so that the technology we provide can be fair. And so here is the ideal place we want to be, where your English capability and the multilingual capability are both very good. The size of the circle is the model size. So if you want to do streamlined deployment at scale, then the model size is important. So the pink circle is ours. So it's on par with models developed at Meta and Qianwen models. But it's smaller. So we're trying to move to the red circle, and this is for the language understanding and reasoning tasks. For language generation, we see a similar trend, and again, the ideal is here. And so ours is the pink model, where we are better at multilingual capabilities a little bit, and reasonably small, 4 billion model. And so we want to reach the ideal, and glad to be performing on par and a bit better on the multilingual sense compared to North American and Chinese models. So here are some highlights from the different multimodality aspects. The first is for the picture, image understanding part. Because it's for children, a lot of lessons needs to be embedded in where you don't want children throwing sand at each other. When there's a child that's sad, you want to know that we should comfort and try to help out. And it's very dangerous to go on the stairs and fight at the same time. So I'll show some examples later. On the speech understanding side here, basically what we're showing is for Malay and Tamil, when we benchmark with OpenAI's Whisper model, our error rates are lower. Ours is the orange, and the blue is OpenAI's. And then we have different types of test sets where some are adult speech, some are Singaporean children's speech, some are Malaysian adult speech. And then some are Indian populations that speak Tamil. On the third part is the multilingual text LM part, where we do an LM as a judge to help to evaluate which model is preferred, Qianwen's model, Q1's model, or our model. So the dark blue means it favors ours. So we see for Tamil and Malay, ours is favored. For Chinese, we do equally well as Q1, and Q1 derived from Chinese models, so they're already pretty good. So here, I want to show a couple examples. The first one is Singa Kids AI Tutor for Science. This one is in English, and the other two will be in other languages.
Hello. Let's think about how a rainbow is formed. We know there is both rain and sunshine when we see a rainbow. What do you think happens to the sunlight when it hits a raindrop?
I don't know.
That's okay. Let's think about it together. When sunlight enters a raindrop, it's like the light goes on a little adventure inside the raindrop. What do you think happens to the light inside the raindrop?
The light disappeared.
Not exactly. The light doesn't disappear, but it does change. What do you think happens to the light when it enters the raindrop?
It's too difficult. I don't know.
That's okay. Let's simplify it. When sunlight enters a raindrop, it bends, which is like curving or changing direction. Inside the raindrop, the light breaks into many colors, like when you use a prism in science class. Can you think of why we see different colors instead of just one color?
So different from humans, AI is very, very patient. So it doesn't get upset when the child keeps saying, I don't know, or doesn't talk. And then it can generate explanations in the way that the child can understand better. And so this is one example of scaffolded question and explanation generation. And then I wanted to show another thing on the empathetic reasoning part of how we want scaffolded guidance to be scalable to help this. And so here is one example where we found when we were doing some trial runs, where so here is a picture of the celebration of the Lunar New Year. So in Singapore, we celebrate it as well. So although the children like the public holidays, they may not really know a lot of the underlying cultural related matters. So in this example, they may not know what are the red balls hanging from the wall are. So these are lanterns. So maybe after a couple tries, you realize, hey, the child doesn't know the vocabulary. So instead of spoon feeding, you guess that child might have heard it before, and you want to be a little more suggestive. So you might use tag questions in English and say, this is a lantern, isn't it? So in English, it sounds perfectly fine. But when you translate it to Mandarin, 这是灯笼，不是吗? In this cultural context, it might sound like scolding. It might sound like, oh, you don't know such a simple thing? How stupid are you? Then you're actually doing the exact opposite of what you intended to do. You're actually disencouraging the child to learn. And so then another way to say it would be, this is a lantern, right? So when you translate this to Chinese, 这是灯笼，对吗? So in this context, it sounds much more encouraging and it's a more appropriate way to guide students to speak in Mandarin. And so this is one example. And then we saw similar patterns of this westernized Mandarin in Malay and Tamil as well. And so this probed us to think of more systematic ways to address these kinds of cultural issues. So this is an example to show that language and culture, although very interrelated, still have differences. And just addressing the language part alone doesn't necessarily help with the culture part. And if we want to do this at scale, a lot more thinking and training needs to go in. And so this is one example where we learned a lot from a real-world deployment trial. So now I want to show some examples for the Chinese and Malay ones. I think there are people that understand Chinese and Malay, or the Malay is very similar to Indonesian. So let's show the Chinese one first.
小朋友，我们来看这张图片。你看到左边有一个男孩在做什么吗？
男孩在哭。
很好，你知道为什么男孩在哭吗？
他好像摔倒了。
对，他可能摔倒了。你看，他的姐姐在做什么呢？
我看不出来。
没关系，我们再仔细看看。姐姐的手在男孩身上，她的表情是怎样的？
他很难过。
对，她很难过。姐姐在做什么让男孩不难过呢？
姐姐在安慰他。
非常好，现在我们来看右边，你看到那个女孩在玩什么吗？
滑梯。
对，她在玩滑梯。你觉得她的心情怎么样？
小女孩看起来很开心。
对，她看起来很开心。你能再说一遍开心吗？
开心。
太棒了！今天我们学了3个词：安慰、滑梯和开心。继续努力哦。
The Malay one, actually, this is an older example. We have newer Malay speech generation, but we'll show this first because this voice was previously deployed for teachers' voices in schools.
Baiklah, mari kita lihat gambar ini bersama-sama. Di bahagian kiri gambar, apa yang kamu nampak?
Seorang budak lelaki menangis.
Betul. Siapa yang sedang menolong budak lelaki itu?
Seorang budak perempuan.
Bagus. Sekarang mari kita lihat di bahagian kanan gambar. Apa yang kamu nampak di situ?
Seorang budak perempuan turun gelungsung.
Ya, betul. Bagaimana perasaannya budak perempuan itu?
Dia nampak gembira.
Bagus sekali. Jadi, perikah kamu sebut dua perkataan baru yang kita pelajari hari ini?
Gelongsor dan menolong.
Bagus.
So I will skip the Tamil one. I think no one here speaks Tamil, and we have some time constraints. And so here, quickly summarizing, so for children, they're a minority population amongst AI users, and so their needs could be overlooked. And so here we looked at the education use case. And then again, for this case, actually the audio speech modality is quite key to enrich the multimodal reasoning. And we also looked at some of the languages outside North America to give examples of how we might want to prepare for global needs better. And also, in this case, because we're talking about scalable deployment from the public sector, so lightweight models are useful, and this is taken into consideration when we develop our models. So the third one is a healthcare example where intelligence-informed analysis is very key for decision making. And so here we need to work also very closely with the domain experts. And they help us form the grounding part. So here, one example I want to show is Shodai telehealth agents for diabetes. Shodai I previously mentioned in English, it means less sugar. They're very key for diabetes management. On the technical side, it means sharing information with users on diabetes actions and intervention. So basically, for a lot of chronic disease patients, after they're discharged home, we have a program where the nurses will call in for telehealth support. But it could be very time-consuming, so it's also together with apps that can collect compliance information so that when the nurse calls, it has more information to make the conversations more sharpened for the clinical needs of the patient. So this agent is under clinical evaluation at SingHealth, and then I'm going to give some examples of the conversations for you to listen. So so here it's spoken Singlish discourse with clinical and social grounding.
There's some swelling on the feet.
Can you help me? Can you help me?
There's some swelling on the feet.
Yeah.
Oh dear. But the fluid part okay or not? The fluid okay or not? Fluid, he sometimes don't know. Don't want to listen. I become very firm with him. Oh, very firm ah. Oh dear. Because I say this cannot go on. Oh wow, really very stressful on your part ah. What to do? Yeah, what to do? You are the wife ah. So how Because and he takes anything he wants, put ice on it. Ayo. Oh, icy love icy drink. Need to watch out all the extra fluid, you know. Yeah, so I told him, I said no more cold drink for you
To actually the patient's spouse, because this patient may not always be able to come to the phone or might be too ill to answer the phone. And so I'm going to I color-coded for the spoken part, the Singlish part, the clinical grounding and social grounding part. So it was a lot of colors in the previous slide. So here I'll go through one by one. So spoken discourse is very different from text discourse. So there's a lot of natural fluencies like fillers, discourse particles, interjections, false starts. So you might start a sentence and then realize you're saying something wrong and continue midway. You might do that in the middle of a word, like fluid here. So I color-coded in purple. And so these are very natural when we're talking. And then for Singlish, there is, some of it is of the spoken characteristics mentioned are overlapping with Singlish. So Singlish is an example of how multilingual slangs and syntax could intermix. And so here we show examples of the grammar. It may not follow subject-verb agreement in standard English. It could use discourse particles from other languages. And then it could also, some phrases like what to do. This one in English translation is, oh well. It kind of means like, well, I guess that's life. I cannot really change this. But you kind of given up changing it but it's something kind of bad. And then, the Tamil's not showing here, but ayo actually has many roots. One is Tamil, and then I think in Chinese and Malay languages we also use it. So for the social grounding part, this is very key. So look at the nurse's response. A lot of it is very pink. And so this specifies the social grounding because when we talk with one another, we want other people to feel like we're listening. We want to show that they are being heard and we understand them. So there are different techniques we use very intuitively on the social front. So this includes back channeling. And then there's a lot of repetition. And it's confirming that we hear you. And so this is very different from written discourse where this will be seen as, why is there so much redundant information? Because when you only look at it from a more standard document perspective, you don't realize speech is a very social activity. There's a lot of back and forth to make sure the other person understands. And we also don't have so much working memory at one go. So you have to make the sentences very short and do a lot of repetitions. And so here the key thing is the social grounding is interlaced with the clinical grounding. So the clinical grounding, I make it green here. So basically whether you're heart failure or diabetes, one key clinical part that you need to be careful of is fluid overload. If there's too much fluid, there might be other risks that you need to be aware of. So it might present itself as swelling on the feet, at the limbs when there's swelling, so that's not a good sign. So then that's why the nurse zoomed in to talk about the fluid part. And then this brings in different complications. When you want to drink with ice, then you get extra water intake. So these are things that you need clinical knowledge to do the grounding, and you need it to be done in a socially accepted way. So this could, if you're talking to the patient directly, you might also need to do social grounding in a similar way, or else the patient won't want to listen to you. Yeah, so these are different types of spoken language phenomenon that may not always be integrated well into the AI models. And here I show some examples of where we can zoom in to do more research. So all of this helps enable us to generalize disease management, especially for chronic disease. So in addition to the embodied sensory signals of speech, we could also bring in wearables, vital signs, diet and nutrition, and medical history to help enrich our understanding, and this can help empower more timely clinical care support. So the takeaway message is here, we might use a lot of other information, so speech and audio and sensors, to help us better contextualize and do better decision making. And a lot of these could be important for Asian populations, and a lot of the healthcare studies might also be more centered around Caucasian patients. So we also want to help model the Asian patient side well. And here, domain expertise is also very key in grounding the AI reasoning, so working closely with the domain experts is important. But if we can do this, then we can have a better human-AI collaboration to enable precision health. So this is a summary, and I will conclude the talk. Yeah, thank you.
So I think it's this is a really excellent talk. Thank you very much. But limited, but maybe I may take one question. Yes.
Very interesting talk and presentation. I just want to have a quick questions. I participated in the Southeast Asia Language in One Network Sea Lions, and I see here the Merah Lion. Is there any relations or connections out of this effort? Right.
Which model national program in Singapore. So we work with the Sea Lion team. So for the so our part is more focused on the multimodal aspect, where so that's where we bring in the speech modality, and then the Sea Lion team focuses more on the text part. So we are partners in this endeavor. Yes.
So should we stop at this moment? Or one more question? Oh, so we still have a question. So but I have a question, so let me use my time. So I think the key is grounding, right? So social grounding and the physical symbol grounding and also mutual grounding. So do you think it's if we continue to data collection in a similar way and put the data into the LLM, so whether the foundational LLM can capture this kind of all of the groundings in the same way, or we need a more kind of sophisticated way to teach LLM to know what is the grounding?
Yeah, I think this is a great question. Grounding can come in from different perspectives, and I think we may not be doing enough to know how to answer your question, but because I think so, if it's different domains, then it might need to be manifested in different ways. But I think from speech researchers' side, we are actually quite attuned to it because we often know during test time and training there are different types of differences and try to bridge the gap. So I think our experience could help also, whether it's domain experts or people working on robotics, to help bring in some of that perspective, because we have the experience from more sensory type of data, and also a lot more applications have been developed. And then on the other side, we have a strong link to the natural language processing side of the text modeling aspect, so our experience could be very helpful when we do this kind of grounding.
Some grounding needs the embodiment and the physical relationship to the physical world. So,
yes.
So then the censoring is possible. So we just extend the speech or the microphone or video or something. But to make an action, not only text or speech, we need more robotics something.
Yeah, I think our experience on the dialogue modeling side is like a good example for robotics to learn, because the dialogue system is actually trying to interact with the real world, but in just maybe the speech modality that spans the social aspect. But for robotics, you might need more than that. But ours has, for the past 10 years, has worked reasonably well for the transition. So that can help from the machine learning side. I feel that for embodied AI, then they can take reference from that for how to frame the reinforcement learning part, but slowly add in more of the modalities.
Yeah, okay, thank you very much. So we are expecting a bright future for technology.
Yes. Yeah.
Okay, thank you very much. I'm sorry that I used my QA time for my question.
Thank you.
Again, thank you very much, keynote speaker. So you will be in the dinner today.
Yes, I'll be here.
So if you have a question, please ask in person.
I'll be here at lunch as well, coffee breaks.
Thank you very much.
Thank you very much for Dr. Nancy F. Chen and Professor Nakamura. Please remain at the stage area for a while for Dr. Chen and Professor Nakamura, as we would like to present a token of appreciation for both of our keynote speaker and also the moderator. And for this, may I invite Professor Sakriani Sakti to present the token of appreciation. Yeah, so Dr. Chen, please, we would like to present the token of appreciation. This okay, yeah, it's okay. So first, we will present the token of appreciation to Dr. Nancy Chen. Yes, please give a round of applause to our keynote speaker. Okay, and here another souvenir, yeah. Thank you. And next, we would also like to extend our heartfelt gratitude to our moderator, Professor Satoshi Nakamura, for leading this keynote session. Please give a round of applause. Okay, thank you very much. And now before we move to the next agenda, we would like to take a group picture to capture this wonderful moment together. So to all participants, we invite you to go to the stage as well as our speakers and also the committee. We will have a group picture as some of the participants just arrived and joined the conference this day, so let's capture this moment together with a group picture. So please come to the stage, everyone. May the student assistant help to remove the seat first? Yeah. Yeah, I think we can do it here, and some might also on the upper stage. Yeah, maybe Prof. Hamam, Bu Sakarini, Dr. Nancy, at the table. There's still, room on the left side. I think some can move, a bit here, Okay, I think everyone is ready. The photographer, could you count? Oh, with Duta Wacana sign, Duta Wacana logo like this. Okay, thank you very much. You may return to your seat. So, ladies and gentlemen, now we will take a short coffee break. Refreshments are available at the back left and right of this venue. So please enjoy some coffee or tea and take the moment to relax and network with fellow participants. Our next session, the oral session 4, will begin promptly at 10:10 a.m. So we kindly ask participants to return to your table few minutes before 10:10, so we can start the session on time. Thank you, and please enjoy your coffee break.
Recording stopped.
Jakarta, yuk, berangkat sekarang yuk, Jakarta yuk.
Hati-hati ya.
Ibu baik-baik di rumah ya Bu. Pamit ya.
Selamat pagi Bu. Selamat pagi Mbak. Pagi Pak.
Ini adalah kisah kami tentang harapan dan mimpi akan sebuah tempat yang penuh kemajuan dan inovasi. Kami tak hanya menuliskan barisan kode dan coretan tanpa arti, tapi solusi nyata untuk berjuta kehidupan setiap hari. Dan ini bukan hanya soal membangun aplikasi, tapi membangun sebuah warisan. Dan kami bukan sekedar talenta. Kami adalah penulis masa depan. Kami percaya masa depan teknologi harus dikuasai negeri sendiri dan dibangun oleh anak bangsa yang berani bermimpi.
Fokus untuk tenaga-tenaga ini handal di bidang science, technology, engineering, dan mathematics.
Dan ini bukan sekedar tempat kami bekerja, tapi juga wadah untuk belajar dan membuka cakrawala dunia. Tempat kami menggantungkan harapan, memberi layanan, dan membangun jembatan masa depan.
You're so funny. You are so funny. You are so funny. You're so funny. You're so funny. You're so funny. You are so funny.